This next speaker works in the Languages, Optimization, and Libraries team at Google, where they lead a team working to enable faster speed iteration and deployment of hardware accelerators. In their free time, they work on projects like I'm-Tomu, a range of development boards that fit inside your USB port. Their talk today will demonstrate the possibilities of a fully open source FPGA toolchain. Please welcome to the Hackaday Super Conference stage, Tim Mithro Ansell.
Hi, I'm Tim and I'll be giving this talk. I have 115 slides and about 30 minutes, so I brought something to help me along with that. So I'm talking about FPGAs. You all have a badge with FPGAs, and I like to think of FPGAs as converting hardware into software, and I self-identify as a software developer. You need a toolchain that matches your software development type lifestyle. So it's important to note, though, that SymbiFlow is the name of a group of projects, and it doesn't really own any of them. It collaborates and integrates and brings people together, but there's a huge number of people working on this project. In many ways, I'm just a project manager and don't do anything interesting except help people get their work done. People like Clifford Wolf from Symbiotic EDA and Dave Shah have made extremely huge contributions, and it's important to understand that, I might be up here presenting, but this is mostly not work I have done. They're just more shy than I am. And it's also important to understand because we need you to help us push this toolchain forward. So SymbiFlow aims to be completely open source, Verilog to Bitstream, and a Bitstream is something you can load on the FPGA. It aims to be cross-platform, multi-platform, support wide variety of different vendors, and it's designed to be pluggable and interchangeable so that you can choose which parts you want to use. And this is kind of different from any other tooling out there at the moment because it's designed to target FPGA types from multiple different vendors. And we hope that eventually it supports all FPGAs. Big FPGAs like Intel x86 size things down to tiny little microcontrollers like the ARM teeny little things that you're used to. And in the same way you can use GCC for all that range, we want this to be the same. And FPGAs come in all sizes. This is a giant FPGA, probably something found in data centers or in a bit mining rig catching on fire. And these are really pricey. They're like the same price as an Intel CPU. But they also come in really tiny packages and very accessible sizes. This is a really small FPGA dev board, and it fits inside your USB port. And it's priced in the same type of category as a tiny little ARM microcontroller, a couple of bucks type range. The badge you have has an FPGA on it. It's kind of what we would call a mid-size FPGA these days. And it's kind of in a similar class to an embedded Linux microcontroller, kind of the $5 to $10 range type thing. And both the tiny FPGA in the FOMU and the FPGA found on your badge come from a company called Lattice Semiconductor. The thing is, if you look at the FPGA market space and divide it up, you tend to get a pie chart like this. The thing is that on this pie chart, neither of these big slices are Lattice. Lattice isn't even mentioned on this chart. and is frequently not even mentioned on these type of charts. Lattice is included in that green slice called Other. They only have a very small market share. The big slice that has kind of 50% of the market is a company called Xilinx. You can kind of think of them as the Intel of the FPGA world. The other big pie slice is this group called Altera, which is actually Intel now. So Intel's kind of the AMD of the FPGA world. Xilinx is definitely the big powerhouse in the FPGA market. They have a huge range with a lot of different and highly advanced parts. And this is kind of what their product market diagram looks like at the moment. Your FPGAs get newer as you go across and bigger and more expensive as you go up to paying $10,000 a chip. They also have a product line called Zinc, which takes an FPGA and smashes it together with an ARM microcontroller. Confusingly, the Zincs have different types of FPGAs in them, but are not named in any logical way that will let you tell that. And so, if you're looking at the Xilinx parts and comparing them to the Lattice parts that you're familiar with from the badge, the ECP5 is kind of similar to a Spartan 7 type device, and the ECP5 5G, which has high-speed transceivers, is kind of similar to the Arctic 7 series from Xilinx. The interesting thing is Xilinx don't really have a reasonable equivalent to the Lattice ICE40 that's found in the FOMU. If you want a FOMU type device, you really need to get this part from Lattice. And Lattice don't have a real equivalent to the Zinc, which takes an ARM and FPGA, smashes it together into one chip. And this is why it's really important to have multi-vendor support in the same toolchain so that you don't have to change your toolchain based on which FPGA you want to use. And so that's kind of what we call the 7 series of Xilinx parts, the Spartan 7, Arctic 7, and the Zincs with those equivalent FPGAs internally. And they kind of sit there. They're not the most modern stuff from Xilinx, but they're definitely not old either. And we often abbreviate it to XE7. So as I mentioned, SymbiFlow is aiming to be multi-platform for all projects, big and small. And if I came to you and was trying to sell you this new awesome C compiler, you'd think it was pretty niche if it didn't support x86 at all. And so that's why the SymbiFlow project really needs to support Xilinx parts, because they are the most commonly available parts out there. There's a problem though. FPGA vendors do not provide any documentation on how their parts work that are suitable for building tools for those parts. So that's a pain. And so if we look at the SymbiFlow project diagram, one of the first things we have to do for any part is document the bitstream for that part. Document how the project, how the FPGA works and how you configure it. SymbiFlow currently has 3 bitstream documentation projects. IceStorm is for the little ICE40 because, ice and ice. ECP5 is Project Trellis because a lattice is a type of trellis. And Project X-Ray is for the Series 7 parts. And the kind of cool thing about Project X-Ray is because all of the Series 7 parts from Xilinx share a lot of common architecture, Project X-Ray targets all of them. But what we do most of our testing on is the Arctic 7. And this is an Arctic 750T and what it looks like internally. Back at the start of 2018, this is kind of what the stats looked like. We had really good documentation for an ICE40, And we had some initial documentation for the 7 series type thing. You could probably, with some force, do an IoT level design at the start of 2018. And interesting to note is that at the start of 2018, there was no real ECP5 documentation. But this is what it looked like by the end of 2018. For Xilinx parts, we had enough to do these IoT designs, but we didn't really advertise this because there was still a huge set of limitations. If you look at that diagram again, at the end of 2018, we knew all the green stuff. There's still quite a lot of red stuff there, which you need if you want to do anything advanced. The interesting thing is in 2018, the whole of the ECP5 was documented, and that was done by a guy called David Shah. David Shah is an absolute powerhouse of the open source FPGA community and is probably the person most responsible for building an open source tool for the ECP5, which is used on your badge. Recently, he started a Patreon, so if you have some spare money, please sign up and help him. But you didn't come here to talk about ECP5, you came to talk about Series 7 stuff. And so our target for, at the start of 2019, was to take what we had built and enable a full big Linux system running on the fabric. And so that's Ethernet and DDR memory. So by the middle of 2019, we had made significant progress and we actually understood all the bits required for that Linux design. As well, a group from a company called Amp Micro had expanded our Series 7 support to also work with Zinc. Pretty much by the middle of this year, there were only 2 major things that we hadn't got good understanding of, and they were the DSPs and the high-speed transceivers, or GDPs as we frequently call it. So going back to this tile view, this is where we were at 2018, end of 2018, and this is where we were at the middle of 2019. The blue blocks are the DSP blocks. There's kind of a couple of columns of there. There's some advanced I/O modes that we haven't quite documented yet, and these are the high-speed transceivers. And so that's kind of the summary of the Bitstream documentation. So once you have the Bitstream documentation, you're done right. Well, sadly, no. That's just like having an x86 manual for how the CPU executes instructions. You still need to be able to generate the designs. An important part of that is a thing called place and route. And remember how I said that SymbiFlow is trying to be pluggable and interchangeable? We actually have 2 timing-driven place and route solutions that we've been working on. The one that you've been probably playing with through the badge is a thing called NextPNR, and it strongly targets the lattice parts at the moment. Again, this project has been driven forward extremely heavily by Dave Shah. And your badge basically was possible because of his work on NextPNR. So really, if you do have spare money, please do sign up for his Patreon. For the Series 7, though, we use a different place and route tool called Verilog to routing, or VTR, VPR, depending on how you talk about it. And the interesting thing about VTR is, again, this is not most of my work. It's primarily developed by a university called the University of Toronto, and it was developed to be an academic research tool for researching new FPGA types. And so what we've been doing is working with them to actually target real hardware rather than research hardware. And to make this all work, we use a repository called architecture definitions, which takes the information from Project X-Ray and generates the information needed for Verilog to routing. That's still not enough though. Before you can do place and route, you have to do synthesis. And for synthesis, looking at this diagram, it kind of sits here. So I've kind of been going backwards along the diagram. For synthesis, we use Yosys. And again, Yosys is not something I've developed. It was developed mainly by Clifford Wolf, who now leads a team at Symbiotic EDA to do it. And the interesting thing about Yosys is it's a pretty essential part of the whole ecosystem for a lot of different things. And so this is a more complicated version of the diagram. And in 2019, there was a big effort to improve Yosys for synthesis going into Vivado for place and route. So you can use Yosys, which is open source, and Vivado, which is the closed source tool provided by the vendor, to do a generation of a bitstream. On a side note, Yosys has also been improved for Xilinx's older ISE tools. So you can use the same front end for multiple different vendor backends. And the other big thing that's happened in 2019 is better inference support. This was mainly led by a person called Eddie Hong, and what inference support means is that it takes something like this multiply operation and maps it to DSP tiles so that you can use some more of the advanced functionality inside the FPGA. At the start of 2019, Yosys didn't have much ability to inference DSPs at all. By the middle of this year, we had support, and quite good support now. And the interesting thing is, because Yosys is used as the front end for both the 7 series and the ladder stuff, a lot of the ladder stuff was pulled forward as well. And this is a really good example of how the SymbiFlow community is kind of working well together. So what you've all been waiting for now is, what about Linux on 7 series? Take something like this ARDI board, which has DDR memory and has 100 megabit Ethernet. Could you build a design that works? If you use Yosys into the commercial tools, that does work, and that kind of gets you halfway. But what you really want to know is whether it works for SymbiFlow. So, can I get a drum roll? Come on. I'm afraid to disappoint you though, the answer's no. But it is the 14th of November today. You might notice that the 14th of November is not the end of the year. And we're getting very close. I believe that by the end of this year, we will have this working. We're pushing hard to make it happen, and it seems entirely realistic that we can make it happen. And you can help make it happen by contributing. And remember how I said place and route, we had 2 systems, and how productive Dave Shah has been with NextPNR? He wasn't satisfied with just targeting ladder stuff, so he's also started doing some experimental work on importing Project X-Ray into NextPNR. It's not ready for users, but if you have some spare money, please donate to him so that he can make that a reality, because having multiple implementations is a really great way to make both better. So that's the current state of RTX 7 and Series 7 support in SymbiFlow. An important thing to remember though is this was mostly just done this year. Things are moving really fast. You should be using upstream, basically head of everything. I have seeing people like Dave Shah and Clifford respond to pull requests, to bug requests within like 5 minutes of you logging them, and then if you clone the update, you've buggers fixed. So if you're watching this at home on YouTube and it's no longer the 17th of November, the information in this is probably out of date. So go and find a newer presentation from me that actually has the later information. And I want to reiterate that ultimately SymbiFlow is a group of people. It has heroes like Dave Shah who are doing awesome work that we support, but it also has many other people doing many other things. And so you can contribute too. One place we would love your contribution is in helping document one of the most complicated tiles, which is the DSP slice. They show it normally like this, but internally it's actually like this. So it's quite complicated. And we really need good simulation models and Bitstream documentation. And so that's one of the key things that you could help with, but I'm pretty sure everyone in this room could contribute in some way. If you know Python, you can help. All our scripts are written in Python. If you know C++, pretty much all our tooling is written in C and C++. If you know Tickle, I'm sorry that you do, but we would love your help because all the vendor tools use Tickle as a scripting interface. If you know Verilog, I'm also sorry, but we would love your help in writing simulation models for the parts because it's much easier to test things if you have a model to compare to. If you know XML, congratulations for getting to the early 1990s. We're also stuck there in some areas and we need your help with doing things like XML parsing efficiently. If you're more sysadmin or user-focused, we would love your help with packaging with things like Docker and I don't know, whatever the popular packaging method is these days. And we need you to do it in such a way that every time we push, you get a new version because everything's moving so fast. And if you're listening to me, you probably know English. And we would love help with things like documentation and logging bugs about where things aren't clear and logging bugs with this doesn't work. And helping solve them, being on the IRC channel and helping new users go through the same thing that you did, spreading the word. If you have time, I am sure I can find something that I can get you to do. So this is especially students who think they don't know anything. You're actually a prime candidate for a whole bunch of things because we're very much targeting users who have not done this before, users from a software background. And if you don't have time but happen to be like me and have a well-paying job at a big IT corporate, you can probably spare the money to fund Dave, and he does more, like he's kind of equivalent to 10 people. The other thing is, if you contribute to the SymbiFlow project, I will send you hardware. This is a FPGA Tomu. I have sent these to every continent apart from Antarctica at the moment. I don't know if Post goes to Antarctica, but I will send you hardware if you contribute. I also have here somewhere. The problem with the Tomu is it's quite small. There's about 150 here. I also have Spartan 6 boards. And ARTI boards. And the deal is you need to use them for something. If you're doing something cool with them, I'm quite happy to give people hardware. Like hardware for me with a Silicon Valley, salary, and not having any kids, not having a wife or anything like that, not having a mortgage, means or drinking, I don't drink at all, means that this is quite easy for me to do. And if not having hardware is blocking you from contributing, I would love to remove that. So do something cool, come and chat to me and convince me that you'll do something cool. Send me pull requests and I'll send you hardware. That's kind of the deal. And so, any questions? I'm kind of at the end. You've got the status. We would love to see you come join our IRC channel or Slack channel. If you're interested in other types of FPGAs, there are other people working on other projects out there to document other FPGAs. We want to support everything we can. We're definitely heavily focused on Xilinx parts at the moment because of the things I mentioned. And yeah, if you come and chat to me, I will find a task that you can do and you can help drive this forward. So thank you very much. And any questions?